Hi, my name is William Johnson, and I'm representing the Physics 2211 Colliding Objects Lab, which is a lab that I made on my own. This is the introduction for the lab. The purpose of this lab is to observe the law of conservation of momentum through an observational model via tracker and a computational model via GlowScript. I will then compare both of these models to see how external forces and errors cause variations in data. I will then solve to observe whether or not momentum was conserved or not. Quick summary of the results of this lab are that both models lined up very similar in the early time periods, but they differed after the collision. This is most likely due to the force of friction causing negative work on the tennis balls. Also, during the collision, energy may have been lost, causing the computational model to differ. Some key concepts in this lab are Newton's second law of motion and the momentum principle, conservation of momentum, conservation of energy, perfectly elastic, elastic and inelastic collisions, and then point particle and multi-particle systems. Some equations that I use throughout this lab are the velocity update formula, the position update formula, the kinetic energy formula, which is 1 half mv squared, momentum, which is equal to mv, and conservation of momentum, which is p final is equal to p initial when no work is done, no impulse is done. Here are the diagrams that I made for the lab. So I used two tennis balls and they collided. In the first picture, the ball one is at non-zero momentum and ball two is at rest with a zero momentum. And then during the collision, some momentum and some kinetic energy from ball one is transferred to ball two. After the collision, both balls have non-zero momentum. Here is the tracker video for this lab. And then here's my code for the computational model, which identifies the initial conditions. So here are my masses that I inputted. For both balls equal to the same mass. And then the initial position of ball two is inputted there. And the initial position of ball one is inputted there, which I got from the tracker model. And then I inputted the ball one dot velocity and ball two dot velocity, which is the initial velocity of ball one and ball two. Here's the iteration conditions for the first while loop, which is just the updating the position and velocity during the first before collision, prior to the collision. And then I inputted the velocity update formula and the position update formula. Here are the iteration conditions for the second while loop, which is after the collision happened. So which I inputted the velocity update formula, position update formula again. Here's the video of the program running. And then here are the graphs of the comparison of the tracker and GlowScript model. So as you can see, they're pretty similar. This is the X position versus time graph and the Y position over time graph is on the right. As you can see, they're pretty similar, but they start to go off as time goes on. And then same with the Y position. It is kind of similar, but again, just errors caused for some difference in the GlowScript and tracker models. And then here's the results for the ball two, which is just the difference between the tracker and GlowScript models. So especially on this X position versus time graph for the ball two, you can see that it was pretty much the exact same up until about 0.4 seconds, and then it starts to differentiate. And then for the Y position, it does about the same until about 0.4 seconds, and then things start to get messed up due to the not inputting things such as friction or which I'll talk about more throughout this presentation. The conservation of momentum is shown here as P initial is equal to P final. P initial is equal to 0.57 times the initial velocity plus the initial 0.5057 times the initial velocity of ball two, which is just zero velocity. And then here's P final, which is just 0.057 times the final velocity of ball one plus the 0.057 times the initial final velocity of ball two. The momentum was somewhat conserved with errors from rounding, camera distortion, etc. Here is the conservation of kinetic energy. I'll go throughout with that. K initial is equal to K final. And K 1 half mv squared of ball one is equal to 1 half ball mv squared of ball one squared plus 1 half mv squared of ball two. That's just the initial velocity is equal to the initial kinetic energy is equal to the final kinetic energy. So the K final is equal to 0.0955519 joules, and the percentage loss of kinetic energy is therefore negative 69.267%. Therefore, the collision was inelastic, as over half of the kinetic energy was lost.